Hello everyone, JCE Connect. I welcome you all for this particular lecture. In this particular lecture, I'll be solving a problem on tension member, that too single angle connected to the gusset plate, that is bolted uh, connection. So here the problem given as a single angle 100 by 100 by 8 mm connected to a gusset plate at the ends with 20 mm uh, diameter bolts with the connection leg of 200 mm to transfer a tension. Determine the tensile capacity of the joint. So here a single angle of 100 by 100 by 8, that is equal angle section, connected to the gusset plate, and the number of bolts also given here. There are 5 number of bolts provided in a single row. These 5 number of bolts are being using to connect angle section to the gusset plate. The pitch is also given, that is a 50, and edge distances are also given, that is a 40 and 40 on either side. Then leg sizes are 100 and 100 and 100, that is equal angle size. Then the figure is shown here. Then to calculate the tensile capacity of the joint, we need to calculate uh, three things here, that is a cross section yielding, then net section rupture, and block shears. So out of these three, whichever comes to be the least, that is to be considered as design tensile capacity of the joint. So in that, here the connection details are been given. This is the connection details, and all the dimensions are in millimeter. And this 60 and 40, whatever they mentioned here, this one, this 60 and 40, these things we have to take from the ISI handbook. Means from the heel till the center of the bolt hole, what is the distance, or from the toe to center of the bolt hole, what is the distance. So these things for particular uh, width of the angle leg, these distances are been given, that is gauge distances are been given. You have to refer ISI handbook for this one, or else they will be given in a problem itself. Then by taking those distances, you have to solve the problems. Next, here as I said, the design or the tensile capacity of the joint will be the list of three modes of failure, that is cross section yielding, net section rupture, and the block shear strength. So let us calculate the first strength, that is a cross section yielding. The cross section yielding, this is the formula we use. So this formula is given in IS 800 2007, that is this TDZ formula. This formula, it is there in IS 800 2007, page number 32, 32 and 33. If you refer, you will get this formula. This formula represents the cross section yielding formula. So Az into Fi divided by gamma MO, where Fi is 250 for the plate material, that is the yield stress of the material. Gamma MO is the partial safety factor for the material. When you substitute these all in this uh, uh, formula, you'll get the area, this one, and gross area of the angle section you will get from the steel table. This you have to refer steel table for getting the area. So when you refer a steel table, you will get the area of the angle section. Substitute in this formula and you will be getting the gross area. Next, then after substituting, you will get the uh, design tensile strength considering the uh, yielding as a criteria. This is 349.77 kilonewton you will get. Then the next thing is you have to calculate net section rupture. So net section rupture, again you will be having this formula in a code book. Please refer the code book. This is the formula you will get in a code. This formula. This is for single angle section. So in IS 800-2007 they clearly mentioned this formula. Please refer that formula. And if it is only plate connected to the gusset plate, this formula will be using, and if it is a single angle connected, and one more formula will be adding, this one, because the angle section is connecting like this. It is will be connecting like this to the gusset plate, where one leg is connected to the gusset plate like this and other leg is outstanding, not connected to the gusset plate. So the net tensile uh, force or the uh, tensile strength will be connected leg strength plus outstanding leg strength. This is a connected leg strength plus outstanding leg strength. Then this beta is for correction factor. So as we know, the diameter of bolt is given 20 mm. So plus 2 mm you have to add, that is for a clearance of hole, that is 20, that becomes 22 mm. And you know how to calculate the net connected leg area. So this is the figure given here. So from this you have to calculate the net connected leg area. So the formula given here is this formula. I already explained about this, how it comes in my previous lecture. Please go through that. Then calculate the net connected leg area. Then also calculate the gross outstanding leg area. Once you get ANC and AZO, then calculate a beta. Beta is a correction factor. So this formula also you get from the code. Substitute all the values in this formula. So here in beta, W is the 100 mm, that is outstanding leg width, and T is the thickness, Fi is the yield stress, then Fe is the ultimate stress, then Bs is the shear lag width, that is given W plus Wi minus T, 100 plus 60 minus 8. So calculate this one, substitute back in the above equation, then you will get beta value, and that beta value it should be more than or equal to 0.7 or less than or equal to 1.44. So when you substitute all the values in the above equation, you will be getting, that is beta is 0.96. Then substitute above, then you will be getting TDN. This is the value of TDN, 342.32 kilonewton. Then you calculate block shear strength. Here block shear strength. Calculate block shear strength or block shear value at what load the angle may get block shear failure. So that is a design strength TDB of connection shall be taken as smaller of TDB1 and TDB2. These two formulas you will get in a code again. Just refer a code book. You will get these two formulas in a code. So these are the two modes of failure. So as already explained this regarding these two formulas, so this part is a first mode of failure, second mode of failure. It may fail either yield by yielding, then rupture, and a shear yielding, tensile rupture, and this is a shear rupture and tensile yielding. These are the two modes of failure. So the combined effect of shearing and tearing, what we call as a block shear. The way to calculate these two modes of failure strength, TDB1 and TDB2. Out of these two, whichever is the least, that is to be taken as TDB value. Okay. Then how to calculate AVG, AVN and ATG, ATN. So let us take the angle section. The angle section is like this. This is the angle section. Draw it once again. It's the angle section. It is connected to the gusset plate. Okay. Connected to the gusset plate. This is the angle. Then the failure pattern of this angle, when it fails by block shear, it will be looks like this. That is some segment of the plate material may come out like this by sharing of the bolts. It may come out like this. So this is a failure pattern of that angle section. So here it is shown. So in this case, here this is the plate. When this plate is been subjecting to tensile force, when you apply tensile force, so this part of the plate, so it may cut here. So by cutting the bolts, it may come out, and that failure pattern is given here, this one. So this is a failure pattern. With this failure pattern, you have to calculate what is the shear area and tensile area. So shear area, as I said, shear area to be taken parallel to the load, and tensile area to be taken perpendicular to the load. So parallel to the load, this one, this is to be taken parallel to the load, that represents LV. LV. So how the LV to be taken? From the edge of the section till the last bolt center, bolt hole center, LV. That is taken here as LV equal to 40 plus 50 plus 50 plus 50 plus 50. So that is LV. Then LT to be taken perpendicular to that from the center of the bolt hole till the toe of the angle section. If this is the angle section and this is connected to the gusset plate, this is the bolt, you have to take this from here, this is the toe to the center of the bolt hole as a LT. I hope you understood this one. Suppose this is the angle. These are the bolts provided here. This area, this is under tension. We apply load for this one. Always it is to be taken LT from the center of bolt hole up to the toe of the angle. This is LT. Remember, from the center of bolt hole to the toe of the angle section, not the heel. We will take this as a tensile area and this as a shear area. Mark this one. This is shear area parallel, and perpendicular to this is tensile area. So to take a shear area from the edge of the plate till the last bolt hole center is LV, and perpendicular to that is LT. LV into thickness shear area, LT into thickness tensile area. I hope you understood this one. Then here they have mentioned clearly LT and zoom it. See, this is the LT. So LT to be taken from the center of the bolt hole till the toe of the angle section. This is represent LT, length of tension plane. This length multiplied by thickness. I hope you understood this one. Next, then LV will be again from the edge of the, from here till last, that is LV. Then this one here LV is written, LT is written 100 minus 60, that is 40, and LV will be 40 plus 50 into 4 to 40, thickness is 8 mm. Once you get LV and LT, it is very easy to calculate AVG and AVN. AVG will be LV into T, that is the shear area. Then AVN, so AVN also is AVG is gross area in shear. AVN is a net area in shear. Means after deducting the bolt holes. How many bolt holes are present here? Just I'll mark here. 1 full bolt, 2, 3, 4, 4.5. 4.5 bolts are cut. So this is 4.5 bolt holes are cut. That 4.5 is been taken here. 4 into 1 by 2 into DO into thickness. That is a net area. I hope you understood. 1, 2, 3, 4. 1, 2, 3, 4, and here is half. Half bolt hole has cut. This one, half. Okay, that has been taken here. This one. So I hope you understood this AVG and AVN. So this is very, very important. Calculation of AVG and AVN. Similarly, ATZ is a gross area, LT into T. Then ATN will be what? So how many bolt hole have cut? Half. Here. So when you take from here, this is half has only, it has left out here half. So LT into half into diameter of bolt. So once you get ATZ, ATN, AVG, AVN, substitute in the above equation, that is in TDB1 and TDB2. When you substitute this one, you will be getting TDB1 and TDB2, where TDB will be the least of TDB1 and TDB2. In this, the which is the least one? 264.94 is the least one. So we get TDB 264.98. So finally, the design strength of the member will be what? So fine, you want to take TDC, TDN, and TDB. So whichever is the least among these, that is the tensile strength of the member. I hope you understood this problem. Okay, so please practice this kind of a problem, angle connected to the gusset plate. If it is given equal angle, so one leg of that will be connected to the gusset plate. If it is given unequal angle, they'll mention whether the longer leg is connected to the gusset or the shorter leg is connected to the gusset. According to that, you solve the problems. And remember, we have to calculate the design strength of the member by considering the three modes of failure, that is cross section yielding, net section rupture, and the block shear failure. I hope you understood this problem. Okay, so please practice this type of a problem and try to understand. Thank you.